93 million miles away, something just moved. A burst of energy tore itself off the surface of the sun with the force of 1 billion hydrogen bombs. And right now, it is crossing the gap between that star and this planet. Not in years, not in months, in hours. We gave it a name almost nobody outside a small circle of scientists will ever hear, an X4.2 class solar flare. But the name is no. T, what matters. What matters is what it is dragging behind it, what it might still unleash, and what happens to a civilization built entirely on invisible electricity when the sun decides to remind us who is really in charge. This is the story of a storm that is not supposed to be dangerous. And why, this time, nobody is entirely sure that is true. To understand what is happening right now, you have to understand that the sun is not the calm, unchanging disk we grew up drawing in school. It is a churning ball of plasma, wrapped in a magnetic field so complicated that even the scientists who study it for a living describe it, without irony, as a mess. That magnetic field does not stay still. It twists, it stretches, it gets tangled around itself like a garden hose left in the sun, too. Long. And when it tangles badly enough, it snaps. That snap releases energy that has been building for days or weeks in an instant, a solar flare. The biggest ones can outshine the entire rest of the sun in X-rays for several minutes. Right now, one particular region of the sun's surface has become the most active piece of real estate in the solar system. Scientists have tagged it Sunspot Group 43166, and over the past couple of weeks it has been throwing tantrums almost daily. An X1 flare, then an X1.8, an X2.8, an X1.6, and now the big one, an X4.2, rated Earth-directed, meaning it did not just happen to point at us, it happened while that patch of the sun's surface was aimed almost squarely at our planet. On the flare classification scale, letters matter as much as numbers. C-class flares are minor, barely worth a headline. M-class flares are moderate, capable of some radio disruption. X-class flares are the big leagues, the ones capable of reaching Earth's upper atmosphere and briefly scrambling high-frequency radio communication on the sunlit side of the planet. Each whole letter represents roughly 10 times the energy of the one below it. An X-class flare is not just bigger than an M-class flare. It is an order of magnitude bigger. And this region has now produced 5 X-class flares in a matter of weeks, on top of dozens of strong M-class flares. That is not a quiet sun. That is a sun in one of its most turbulent moods in years. Here is where the story gets strange, and where the real uncertainty begins. Normally, a solar flare of this size comes bundled with something far more physically dangerous, a coronal mass ejection, or CME, an enormous bubble of magnetized plasma, billions of tons of solar material hurled outward into space at speeds that can exceed 1 million miles an hour. If the flare is the flash of a gunshot, the CME is the bullet. The flash arrives in about 8 minutes, the time it takes light to cross from the sun to the Earth. The bullet takes anywhere from 1 to 4 days, but this X4.2 flare, like nearly every major flare this Sunspot Group has produced, did not launch a clearly Earth-directed CME. The plasma erupted and then largely stayed put. Scientists studying the region believe this is because the magnetic field above the sunspot is unusually strong enough to act like a lid, holding most of the ejected material down rather than letting it escape into space. Flare after flare, the pressure builds, and flare after flare, the lid mostly holds. Mostly. One eruption from the same active region, an enormous X8.1 flare, among the strongest recorded this cycle, did manage to punch a coronal mass ejection-free. It was not a picture-perfect direct hit. The bulk of the material is angled somewhat off from Earth's center, but models from U.S. government space weather forecasters project it will begin brushing past Earth's magnetic field in the coming day, with the densest part of the plasma cloud arriving roughly a day after that. It is not moving especially fast, as these things go, somewhere in the neighborhood of 400 kilometers per second, modest by CME standards. Based on that speed and trajectory, the official forecast calls for a G1, or minor, geomagnetic storm, the lowest rung on a 5-step scale that tops out at G5, the kind of planet-wide event associated with historic storms like the Carrington event of 1859, which set telegraph offices on fire and produced aurora as far south as the Caribbean. This is not that. Nobody serious is suggesting it is. But here is the twist that space weather forecasters keep coming back to. The official forecast is a snapshot based on the data available right now. And the data available right now has a habit of being incomplete. Independent confirmation is starting to arrive from an unlikely source, a spacecraft called Solar Orbiter, currently stationed almost directly between the Sun and the Earth, but offset enough to the side that it can sample the incoming solar wind slightly before we DO. In the last day, Solar Orbiter detected a sharp shock. Its onboard magnetometer jumped from a field strength of 17 nanotesla to 33 nanotesla in a short burst a jump of roughly 15 nanotesla in a matter of moments. That is not a subtle reading. That is a spacecraft getting physically shoved by something moving fast. Something is coming. The only real questions are how hard it hits and what else might still be behind it. Because forecasters tracking this region point out something else. Repeated flaring, even without a clean, obvious coronal mass ejection, tends to churn up the solar wind in general. Think of it less like a single wave and more like a stretch of rough seas, more turbulence, more unpredictability, arriving in the same window as the confirmed CME. Several forecasters now believe the storm could run stronger than the official minor rating suggests, potentially reaching G2 or even G3, a strong geomagnetic storm capable of pushing the aurora borealis much farther from the poles than usual and capable of inducing measurable currents in long-distance power transmission lines. And there is a second, more unsettling possibility sitting quietly underneath all of this. Remember that magnetic lid, the one that has been holding most of this active region's eruptions in check. It is still there. Sunspot Group 4366 has continued to grow physically larger, even as its internal magnetic complexity has eased slightly. It remains squarely in what forecasters call Earth's strike zone, the central portion of the visible solar disk from which an eruption travels almost directly toward us. And it is expected to stay in the T-zone for roughly another day and a half before it begins rotating toward the edge of the sun as seen from Earth. That matters, because the fact that a truly major coronal mass ejection has not yet broken free from this region does not mean the plasma isn't there. It means it is still trapped. And every additional X-class flare this region produces is, in effect, one more crack forming in that magnetic lid. If that containment fails cleanly while the active region is still facing Earth, something forecasters say remains entirely possible in the coming 12 to 24 hours, the result would not be a minor storm. It would be a genuinely major eruption aimed directly at us, arriving on top of a solar wind environment that is already stirred up in a planet that has not yet finished absorbing the first wave. Nobody is forecasting a Carrington-level catastrophe. That kind of event remains, thankfully, rare, something that has happened perhaps once or twice in recorded history. But the gap between minor storm, pretty lights, no real consequences, and strong storm, real infrastructure stress is exactly the gap this event is sitting in right now. And that gap is precisely why space weather forecasters, usually a fairly understated group of scientists, are watching this one more closely than they have watched anything in months. So what does a geomagnetic storm actually do once it arrives? At the gentle end, a G1 or G2, the most noticeable effect is also the most beautiful one. Charged particles funnel down along Earth's magnetic field lines toward the poles, colliding with oxygen and nitrogen molecules in the upper atmosphere and making them glow. That glow is the aurora, normally confined to a narrow ring around the Arctic and Antarctic, but during a geomagnetic storm that ring expands. A moderate storm can push the aurora borealis visibly south into the northern United States, southern Canada, and across much of Scandinavia and northern Europe. For skywatchers, this is the payoff. The reason photographers now travel deliberately to high-latitude locations during active solar periods, cameras ready, hoping the forecast holds. But the same particles that paint the sky are also, at larger scales, capable of quiet mischief on the ground. Geomagnetic storms induce small electrical currents in anything long and conductive. Power transmission lines, pipelines, railway signaling systems. During a strong storm, those induced currents can strain transformers, occasionally triggering protective shutdowns. Satellites can experience increased drag as the upper atmosphere heats and expands, subtly altering their orbits. GPS accuracy can degrade for hours at a time. High-frequency radio communication, still relied upon by some aviation and maritime operations, can experience blackouts on the sunlit side of the planet during the flare itself, and disruption for longer during the geomagnetic storm that follows. None of this, at G1 through G3 levels, threatens the kind of society-wide blackout that occasionally makes headlines in worst-case scenario reporting. That level of consequence belongs to the rare, extreme end of the scale, G5 events, the kind measured perhaps once or twice a decade at most, and the kind capable of the sort of widespread transformer damage that utility companies genuinely plan around. But not catastrophic is not the same as nothing. It is simply the space between a light show and a warning. Consider the layers of modern life quietly touched by even a moderate storm. Airlines flying polar routes between North America and Asia sometimes reroute flights slightly farther south during strong geomagnetic activity, both to avoid communication, blackouts near the poles, and to reduce radiation exposure for crew on long, high-latitude flights. Farmers using GPS-guided tractors for precision planting can see their equipment's positioning accuracy drift by feet rather than inches for a few hours. Oil and gas companies monitoring pipelines watch for induced currents that can accelerate corrosion over time. None of these are emergencies. All of them are the kind of small distributed friction that adds up across an economy that has quietly wired itself to depend on a calm sun. This is also why utility companies and satellite operators do not treat space weather forecasts as background noise. Grid operators in regions with a history of geomagnetic sensitivity, Canada, the northern United States, Scandinavia, can take preemptive steps when a strong storm is forecast, adjusting transformer loads or bringing additional reserve capacity online. Satellite operators can place spacecraft into safe modes, temporarily powering down non-essential systems to reduce the risk of damage from a sudden radiation spike. None of it makes headlines. All of it is why the difference between "we saw this coming" and "we did not" tends to matter far more than the storm's numerical rating alone. Earth has weathered far worse than this, and the historical record is the reason scientists are not panicking, even while they are paying close attention. In September of 1859, a British astronomer named Richard Carrington watched an extraordinarily bright flash erupt from a sunspot he happened to be observing. Less than a day later, the resulting geomagnetic storm was so intense that telegraph operator S, across Europe and North America, reported sparks jumping from their equipment, some machines catching fire and others continuing to send messages after operators disconnected them from their batteries entirely, powered by the induced current in the wires themselves. Aurora were reported as far south as Cuba and Hawaii, bright enough that some observers reported being able to read a newspaper by their light at midnight. That event, now known as the Carrington event, remains the benchmark against which every subsequent solar storm is measured, and, notably, the benchmark this current event falls dramatically short of. More recently, in March of 1989, a strong geomagnetic storm induced currents in Quebec's power grid severe enough to trip protective relays and black out the entire province for roughly 9 hours, affecting millions of people in the middle of a Canadian winter. In 2003, a series of storms, nicknamed the Halloween Storms, damaged satellites, disrupted airline navigation and communications, and caused a brief power outage in Sweden. These are the modern reference points forecasters use when trying to calibrate what a G2 or G3 storm might realistically mean for a technologically dependent society. The event unfolding now sits well below any of those thresholds. For now. What keeps forecasters watching closely is not what has already happened, but the fact that the source region has not finished producing. Perhaps the most important thing this event illustrates is not about this particular flare or this particular sunspot group. It is about timing. The sun operates on an 11-year cycle of rising and falling activity, and current evidence suggests we are near or past the peak of the current cycle, a period scientists call solar maximum. During solar maximum, sunspot groups like this one become more common, more complex, and more likely to produce exactly this kind of rapid-fire sequence of major flares. We are, in a very real sense, living through the loud part of the sun's cycle. That has consequences that reach well beyond aurora photography. Modern civilization runs on systems that did not exist the last time the sun was this active. GPS, guided agriculture and aviation, satellite-based financial transaction timing, a power grid that is more interconnected, more automated, and in places, more aging than ever before. Space weather forecasters, working out of agencies with names most people have never heard, monitor this activity around the clock precisely because the consequences of getting caught unprepared have grown alongside our dependence on the technology at risk. This is not a reason for alarm. It is a reason for the same kind of quiet, competent monitoring that meteorologists apply to hurricanes. Tracking a system, refining a forecast as new data arrives, and being honest when that forecast still has real uncertainty attached to it. As of right now, the official forecast still reads G1, minor. The confirmed coronal mass ejection is still projected to arrive within the coming day, with the densest plasma following roughly a day after that. Skywatchers across northern Europe and North America are being told to expect a good, possibly a very good, night for aurora. But underneath that modest official number sits a more complicated picture. An active region that keeps producing major flares without fully releasing its pent-up energy. Independent spacecraft data showing a real shock already in transit, and a strike zone that remains pointed almost directly at us for at least another day. Somewhere above us, tonight, that story is still being written. Not by us, but by a star 93 million miles away that has just reminded an entire planet how small the gap really is between a quiet sky and a storm. We will be watching. So should you.